Welcome to the OpenStax PreCalculus section 1.2 summary. I actually did interval and set builder notation in a different video. So if you're on my website, you can find that. It's listed under bonus material, just because I thought that a lot of people will want to view that differently. A lot of people probably already know that and just want the new topics from this section. Or a lot of people might be going back to this section just to learn that and don't want to wade through all this stuff about domain and range. So that's in a different video. This video is just going to focus on domain and range, which is section 1.2 of our book. And I'll try my best not to screw anything up in here. If I sound a little tired, it's because my beloved Golden State Warriors won the NBA championship last night, and I may have celebrated a little bit, but I guess that's not really your concern. So the first thing we're going to look at is finding the domain of a function algebraically. So in section 1.1, we learned what a function was, this whole idea of a mathematical machine. And we even defined the words domain and range, which you may remember the domain refers to all the possible inputs to your machine, and the range refers to all the possible outputs of your machine. So now what we're going to do is we're going to figure out ways to determine the domain of a function, or really even the domain and the range of a function. It turns out domain's a little easier to figure out than range. So for now we're going to focus mostly on domain, although there's one case where we can figure out domain and range, and when we see that case, we'll get there. So first, algebraically, if I give you a function, if I refer to a machine like f of x equals 3x squared plus 17,364x minus 11,265.7, fine, divided by, I don't know, x plus 1. This is a machine. Right? It's a perfectly good machine. You can take numbers and put it into this machine. I could put the number 2 into this machine, for example. And what I would do is I change all the x's into 2's, and I figure out what number comes out of this machine. However, there are some numbers I cannot put into this machine. So really, when you're trying to figure out the domain of a function algebraically, the way I think about it is, don't think about what numbers you can put into the machine. Think about what numbers you can't put into the machine. You'd be like, wait, you can't why could you not put a number into the machine? Well, some numbers are going to break this machine. And what I mean by break is there'll be some numbers that you could try to put into this machine when the output would be undefined. This machine would not be able to provide you with a number as its output. And that might blow your mind. You'd be like, wait, what do you mean? Like, even if I gave you some nasty fraction or decimal or something, surely somebody could calculate it, right? I mean, what if x was equal to 1.27385? I wouldn't want to square that and multiply it by 3 and then add 17,000 times that number. But somebody could. Some calculator could. So how could this ever go wrong? I'm going to refer to these as our domain rules. And really what the domain rules do is they help you figure out what numbers cannot go into your machine. And so at this point in your mathematical journey, there's really 2 domain rules. Your book doesn't lay it out quite this concretely because I might be kind of cutting some corners. But there's really 2 that you have to look at for what can go wrong. Domain rules. Don't want to divide by 0. A number like 7 divided by 0, for example, is not 0. It's undefined. Hopefully you've learned that in a different class. You do not want to divide by 0. Anything divided by 0 is undefined. So you don't want to put in any numbers that will cause your function to divide by 0. There's a second one. Don't take the square root, or if I'm being really careful, don't take any even root. So when I square root, 4th root, 6th root, 8th root, 3rd root is cool because 3 is an odd number. But any even root, don't take the even root of a negative number. And that's it, kind of. That's it for now. That's it until you learn about things called logarithms, for example, or inverse trig functions. Or there's other things where you have to worry about for domains. But at this point in your mathematical journey, the functions that you will be dealing with, the only things that will go wrong will be these 2 right here. So our domain rules, and maybe I'll even write more later, can be summarized as just there's 2 right now. Don't divide by 0. Don't take the even root of a negative number. So for this specific function, you're looking at it and you see this nasty thing up on top here. But frankly, it doesn't matter what's written up top here because there's no square roots, there's no 4th roots, there's no possible way, there's nothing I could input that would make anything go wrong on the top. I don't see any square roots, I don't see any even roots. I can ignore this second rule for this specific function. However, I could divide by 0. And if you're really clever, I don't even know if you'd have to be really clever. If you're somewhat clever, you might be able to figure out what number you could put into this function that would make you divide by 0. And you're all excited. You're like, yeah, 0, 0. No, it's not 0. Sorry. If you put in 0 for x, you'd have 0 plus 0 minus this weird number divided by 0 plus 1. Right? If you put 0 into this function, that's totally fine. You're dividing by 1. So it's not 0 that breaks this function. It's actually negative 1. Right? So for your domain rules, the only thing that can go wrong here is f of negative 1 is undefined. And the reason why is if you tried putting negative 1 into this machine, you'd get some number up top, and I purposely made this really ugly because the point is you don't even care what number you'd get up top, divided by 0. And any number divided by 0 is undefined. And actually, the only thing that can go wrong is putting in negative 1. And that's a little bit tricky. Like, okay, I see why negative 1 would go wrong, but how can you be so sure that nothing else would go wrong? And that comes back to this list here of my domain rules. I only have 2 of them right now. I don't see any even roots in the problem, so I don't got to worry about this one. So all that can go wrong would be I divide by 0. And you might be able to just look and tell when you're dividing by 0, but there's a better strategy to use. So to figure out when you're dividing by 0, the way I could figure this out is I could take the denominator and set it equal to 0 and then solve this equation. Because any solutions to this equation will be the x coordinates that make the bottom here 0, which would end up being the things that are undefined. And this is a pretty simple equation. You subtract 1 from both sides, you get x equals negative 1. And so this is the only value that is not in your domain. So negative 1 is not in domain. But the reason I went through that and talked about that is I bet I can give you a function where the bottom is ugly enough that you can't just look at it and immediately tell what values are not in your domain. In fact, maybe I'll give you one down here. You can start thinking about it if you feel like it. No, maybe I won't. I'll give you one in a minute. So the point is, if you do things this way, it'll work even with uglier denominators here. X plus 1 equals, take the denominator, set it equal to 0, and solve. Note that I just, by kind of looking at it, determined that I didn't have to worry about my second domain rule here, so I'm really just looking at the first one. So, okay, I'm following you, but what's the answer? All right, so think about, well, I guess I never asked a question. So, question. What is the domain of f? All right, you're told this function up here, f, f of x is equal to this. This rule defines this function f. So what's the domain of f? Well, you just figured out that negative 1 is not in the domain. You figured out what is not your answer. So what is your answer? Well, everything else is your answer. So negative 2, negative 3, 5, 13, pi, 32 sevenths, 0.95, the square root of 2. The point that I'm getting at is there's a lot of numbers in your answer. There's infinitely many numbers in your answer. So you need some special way of writing them, and the special way of writing them is interval and set builder notation, which, as we learned in another video, interval notation would look something like this. Really, maybe I should have drawn a picture first. So in case you're not an expert with interval notation yet, what's going on here is I'm saying my answer is all numbers except for negative 1. So here's kind of my number line. Here's negative 1 right here because I chose to put it there. And what I want is everything except for this. So I want all of these numbers. Goes on forever. I want all of these numbers. I just don't want negative 1. And would it be easier to say my domain is all numbers except for negative 1? Yeah, maybe. But you won't be expressing your answers that way, at least in this section. You'll be expressing your answers either using interval or set builder notation. So if you look at this for interval notation, you recognize that there's 2 different intervals. And this interval, this unbounded interval, we could write as everything from negative infinity all the way up to negative 1. Note that I do not want to include negative 1, hence the parentheses here. And I never want to include negative infinity because it's not a number, it's a concept. So I'll express this interval like this. And then I'll throw down the u for union because I have 2 different intervals that comprise my answer here. And I'll say it's everything from negative 1 up to positive infinity. And again, I do not want to include negative 1 because if I included negative 1, I'd be talking about all of the numbers, but I want to take negative 1 out. Negative 1 is not in my domain. My domain equals this right here. Or if you were set builder type, you could say it's a set of all x such that x is less than negative 1, or the set of all x such that x is greater than negative 1. I don't think your book does this, but I'm going to go ahead and throw you a third one. I could use set builder notation and say it's the set of all x such that x does not equal -1. Ooh, clever. Right? This means the same as this. I think your book tends to use this up here, but just an FYI, this would be just as good. It would explain your answer perfectly to whoever the reader was. And again, I prefer interval notation, so if I were given the freedom to write this however I want, I'd write it like this. I always revert to interval notation, but that's just my personal preference. So there's how you find the domain of a function algebraically. Let me give you one more function. We'll deal with this one pretty quickly. Let's say g of x equals the square root of x plus 2. And we will divide that by maybe x minus 5. This one's tricky, right? Because in this one, your domain rules, both of them apply. You can't take the even root of a negative number. Oh, I got a square root going on here. So this thing, this x plus 2, better not be a negative number. In other words, x plus 2 has to be greater than or equal to 0. All right, inequalities. X plus 2 must be greater than or equal to 0. Note that I did not write the square root here because it's the thing underneath the square root, it's called the radicand, that has to be greater than or equal to 0. So I don't write the square root, I just say that stuff that's under the square root cannot be negative. Mathematically, the way you write cannot be negative is you say it's greater than 0 or equal to 0. In other words, greater than or equal to 0. And if you can solve this inequality, you'd get x is greater than or equal to -2. A quick note on solving inequalities, maybe I don't need to teach that in this section, but as a refresher, essentially you treat this sign just like it's an equal sign unless you multiply or divide both sides of the equation by a negative number. So if I thought it was a good idea to divide both sides by -2 or -3 at some point in my problem solving process, what I would have to do is flip this inequality. Maybe I can demonstrate that. If instead of solving this by subtracting 2 from both sides, I thought for some strange reason it was a good idea to subtract x from both sides, get the x alone on this side, I could. But then I'd have to get x by itself, I'd have to multiply both sides by -1. And that would turn this into a -2 into a positive x. But since I decided it was a good idea over here to multiply both sides of the equation by -1, what I have to do is flip the inequality around. So instead of being greater than or equal to how it started out, now it's less than or equal to here. And note that what I wrote right here is equivalent to this right here. This is saying -2 is less than or equal to x, which is the same as saying x is greater than or equal to -2. To be clear, you'd never solve it this way. That was needlessly complicated. I just wanted to make the point that when you're solving inequalities, the one thing you have to be careful of is when you decide it's a good idea to multiply both sides of the equation by a negative number or divide both sides of the equation by a negative number, which is what I did going from this step to this step. You got to flip the inequality around. At any rate, this whole thing just tells me that my domain, if I'm thinking about the numbers that will not break this machine, I'll start out with all of the numbers that are greater than or equal to -2. In other words, in order to not violate this second rule right here, I'll want my value of x to be greater than or equal to -2. But that's not my answer. And the reason that's not my answer is I still have to worry about this first domain rule. I also cannot divide by 0. So what would make me divide by 0? Well, if x minus 5 equals 0, I'd be dividing by 0. So just like I did up here, I'll take the denominator and set it equal to 0 and solve this equation. And this was another example of one where maybe you didn't need, well, you might have been able to just see that 5 would be bad. 5 would cause trouble. And if you can do that, that's great, but it's a good habit to get into, setting the denominator equal to 0, because I bet I could make something complicated enough that you couldn't just look at it. Okay, so how are you going to write this as your answer? Well, let's start by drawing a picture. Let's draw this little number line. Not necessarily drawn to scale. In fact, not drawn to scale. I want my value of x to be greater than or equal to -2. So I want to include -2 here, and then I want all the numbers greater than or equal to it, with one exception. I do not want x to be equal to 5. Because remember, what I was doing over here in this second column is I was figuring out what values are not in my domain. Not in domain. So these are things you have to keep straight. Over here I figured out what was in my domain. Over here I figured out what was not in my domain. Kind of like up here when I figured -1 was not in my domain. So what I just figured out is x cannot be equal to 5. So really my set looks kind of like this. And in interval notation, the way you write that is you say it's everything from -2 up to 5. I do want to include -2. I do not want to include 5. And then union 5 up to infinity. And again, I do not want to include 5 because 5 should not be in my answer, and I never want to include infinity. And if you had a thing for set builder notation, you could say it's the set of all x such that my value of x is between -2 and 5. And not just between, right? I want it to be greater than or equal to -2, but I want it to be strictly less than. Oh, that's not what I want. Okay. Yeah, this will work. Okay, so I want my x to be between -2 and +5, greater than or equal to -2, less than 5. That's this right here. But that just represents this interval. What about this interval over here? Well, remember with set builder, we put the or down, and we do this again. Set of all x such that x is greater than 5. Interval notation, set builder notation. Okay, one more, I think. At least one more topic, and then I'll call this good. Finding the domain and the range of a function graphically. So what if I drew you a picture of a function? What if my function looked like, I don't know, maybe it starts there, and it goes up to here, and then it comes down to here, and then it goes up to here, and it stops. Fine. Kind of weird looking function, but whatever, I can deal with it. I'll call this thing g. Maybe I should be switching colors here. Here's my function g. Nice thing about a graph is it allows you to easily figure out the domain and the range. Because remember, the domain is the set of all possible inputs, and the inputs are what I graph on the x-axis. So to figure out the domain, I just have to look at these things and figure out what points, what x values have points corresponding on the graph. And so in this specific instance, everything from -4 all the way up to +5, it looks like, would be in my domain. Because anything less than -4, for example, doesn't have any height corresponding with it. But anything anywhere in here has a height corresponding with it all the way until you get up to 5. And then I want to include 5 because this circle is closed. So my domain would be everything from -4 to +5. So I could write that in set builder notation, or I'm just going to stick with interval notation. I think I've talked enough about both. In interval notation, I say it's everything from -4 to +5, not including -4, including +5. Okay, that works out fine for the domain, which is all we've been talking about so far. However, I'm going to spend a second talking about range. Figuring out the range from an equation like this is tricky. It takes a lot of doing. It's something that you'll be learning later on, but we really don't have the machinery to figure out the range of a function like this or a function like this at this point. You might be able to talk yourself into it. You could argue it. It's a really interesting question. It's asking you what numbers could possibly come out if you could put in whatever the hell you want. It's an interesting question, but it's a hard question, and we're going to save it for later on. We'll figure out a clever way to do it later. But for now, algebraically, it's really hard to find the range, which is why we're just finding the domain of a function when things are algebraically given to us. However, if you have the graph of a function, you can figure out both the domain and the range. And the way I'll figure out the domain will be very similar, the range is very similar to what I did with the domain here. The range is all of the possible outputs, and the outputs we graph on the y-axis. So just like the domain is all the possible x's here on my graph, the range would be all the possible y's. And it looks like y values range from -2 here all the way up to +4 here. And you're like, wait, but didn't it go up to, what is that, 2.5 and then back down to 1 and then up to, yeah, it did, but that doesn't matter. Right? The point is that if I'm just concerned with what can come out of this function, the numbers that can come out of this function is everything from -2 up to +4. +2, for example, could come out in many different places. It would come out when I put -2 in, it would come out when I put about 1/2 in, and it would come out when I put 3 in. This function is not one-to-one, to recall some stuff from section 1.1. But you're not concerned with all that. You're just asked the range. You're asked what numbers can come out. And the numbers that can come out is all of the numbers from -2 all the way up to +4. Note that -2 itself cannot come out because of this open circle, but +4 can come out because of this closed circle. So my range would be everything from -2 up to +4. I do want to include +4. I do not want to include -2. There you go. That's the domain and the range of a function when you got it given to you graphically. One last topic that I want to talk about, but I really need a graph for it, so maybe I'll just do it right here, is piecewise functions. So I guess they're a little bit interesting. The idea with a piecewise function is the rule that the function follows depends. So if I give you a function, maybe I'll use h of x, because I've already used f's and g's in this video. And maybe I say that h of x equals x if my value for x is less than or equal to -2, and it equals x squared if my value of x is between -2 and +1, and then maybe my value is equal to -1 if x is greater than 1. Sure. This is what's called a piecewise function. The idea with a piecewise function is the rule that the machine does depends. So you can almost view it, if you really want to go back to the machine pictures, as you sort of have this conveyor belt. Here's your inputs. But then before the machine does its work in here, it sort of splits off. And someone's here sorting them, and this person looks at the number coming in, and if that number is less than or equal to -2, it sends it up here for the machine to do some work. And if that number is between -2 and +1, it sends it here. And if the number is greater than +1, it sends it down here. And then the machine does its work, and then it all comes together on conveyor belt and spits out outputs. So it really is just one machine. It's just the machine is defined by doing these different things. And the way the machine decides what it's going to do is based on this criteria over here. And so as we've seen in this section, if you have the graph of a function, you can figure out its domain and range. And that's really powerful to be able to figure out the domain and the range from the picture. At this point, the only way we have to figure out the range is from the graph of a function. So that kind of begs the question, okay, if I had some weird function like this, some piecewise function, could I graph this function? Because if I did have the graph, I could do a lot of stuff we learned in section 1.1, that I could evaluate the function at given points. I could solve the function. There's a lot you can do with the graph. And what we're learning in 1.2 is you can figure out the domain and the range of a function if you have its graph. But how are you going to come up with the graph of some mess like this? And the key is to go back to your building block functions, your toolkit functions, I think is what your book calls them. And it told you that the graph of a function equals x is this diagonal line right here. That was the ones that maybe you memorized from section 1.1. But I don't just want to draw this diagonal line right here. I only want to draw the diagonal line if x is less than or equal to -2. So here's where x equals -2. I want less than or equal to -2. The graph to follow this, that's almost a diagonal line. Make it look something like that. But that's not my entire graph. That's just taking care of this top part. Then I want to graph something that looks like x squared if my value of x is between -2 and +1. Maybe you remember that x squared is the parabola. It's the U-shaped graph. That's another one that you could either memorize or come up with from the toolkit in section 1.1. So what I want to do is draw this U-shaped graph that is this will give me some guidelines that will help me draw it. Kind of looks something like this. But I want to stop it. I only want it to go between -2 and +1. So here's where x equals -2 and here's where x equals +1. So I don't want to continue this U-shaped graph in both directions. I want to start it here and stop it here. Note that I did not include this point on my graph. That's really important. Right? If I included this point on my graph, I'd have a problem. I wouldn't have a function, because it wouldn't pass the vertical line test. If I drew a vertical line at -2 and this were a closed circle, that vertical line would intersect my graph in more than one spot, which would violate the big criteria for being a function. So I got to leave this circle open. So leave this circle open. This point's not really on your graph. Then even this vertical line only intersects your graph in one spot. And any vertical line would only intersect your graph at one spot, or at most one spot. And then finally, my function is just going to kick out a -1 if x is greater than 1. So this was another of your toolkit functions that told you how to deal with a constant function, I think is the term that it used. And so I'm going to say that when the x-coordinate is greater than 1, I want the height to be equal to -1. So it's going to look something like this. I'll draw an arrow over here to indicate that it goes on forever. And this right here is the graph of this weird piecewise function. Note that -1 is not in the domain of this function. Right? If you look for the x values that have a height corresponding with them in the graph, anything will work except for -1. So often the domains will be everything from -infinity to infinity. Every single point has a height, but that's not the case here, because at +1, this function is undefined. This function, if you put in a positive 1, this function is going to break. It's not going to know what to do. The person sorting this thing right here will be like, it doesn't fit any of those 3 criteria. I guess I got to throw it out. Nothing will be able to come out. So positive 1 is not in the domain of your function. So the way I could write the domain is I could say it's everything but positive 1. In other words, everything from negative infinity up to positive 1, union everything from 1 up to positive infinity. I could also figure out the range of this piecewise function. It's going to be a strange one. If you think about the range, I have heights for all values less than negative 2. So I'm going to want everything from negative infinity up to negative 2. And I'm going to want to include negative 2 because negative 2 is in the range at this point right here. And then I have heights at exactly negative 1. Right? Not less than negative 1, not like negative 1.2 and not negative 0.9, but exactly negative 1. But that's okay, you can write that. If you just want to include the number negative 1, we could say it's everything from negative 1 up to negative 1, including negative 1. Kind of strange, but that's okay, that works. And then I want everything from 0 up to positive 4, so I'm going to need another u here, which I'll write down here just because I'm running out of room. And I do want to include 0 because 0 is in the range. If you put 0 into this machine, exactly 0 will come out. So I do want to include that point. And then I want to go all the way up to 4. Wait, why not go all the way up to 1? Because I don't want to stop it at 1 because I have heights defined at 2, at 3, almost up to 4. Right? All the way up to 4 except not including 4. So I'd say everything from 0 to 4, but I'd leave that open. This down here would be the domain and range of this really complicated piecewise function. So this is getting a little bit crazy, but if you can follow this domain and range of this graph, this is about as bad of a graph as I can imagine. So that's kind of expert level for this section. I'll end this video here.